The Standard Model of Particle Physics, a Comprehensive Overview. Title: The Standard Model of Particle Physics, a Comprehensive Overview. Introduction. The Standard Model of Particle Physics stands as a triumph of human knowledge and understanding. It provides a comprehensive framework for describing the fundamental particles and forces that make up our universe. In this article, we will explore the intricacies of the Standard Model, shedding light on its key components and their interactions. 1. The building blocks. The Standard Model classifies particles into two main categories: fermions and bosons. Fermions are particles that make up matter, while bosons carry the fundamental forces. A. Fermions. Fermions can be further categorized into two groups: quarks and leptons. Quarks are the building blocks of protons and neutrons and come in 6 different flavors: up, down, charm, strange, top, and bottom. Each quark flavor carries a fractional electrical charge. On the other hand, leptons include the stable particles like electrons, muons, and taus, along with their associated neutrinos. B. Bosons. Bosons mediate the forces that govern interactions between particles. In total, there are 4 fundamental forces described by the Standard Model: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. Photons are the mediators of electromagnetism, gluons carry the strong nuclear force, and W and Z bosons carry the weak nuclear force. However, gravity is not currently described within the framework of the Standard Model. 2. Interactions and forces. Understanding interactions between particles is crucial to comprehending the complexity of the universe. The Standard Model describes 3 of the 4 known fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Electromagnetism. Electromagnetism is responsible for interactions involving electrically charged particles. Photons, which are massless particles, mediate this force. The electromagnetic force governs everything from the formation of chemical bonds to the behavior of light. Strong nuclear force. The strong nuclear force is responsible for holding protons and neutrons together within atomic nuclei. Quarks interact through the exchange of massless particles called gluons, which bind quarks with a strong force. The strong nuclear force is crucial for understanding the stability of atomic nuclei. C. Weak nuclear force. The weak nuclear force governs the process of radioactive decay. It is responsible for the transformation of quarks and leptons from one flavor to another. The force is mediated by massive W and Z bosons, which acquire their mass through the Higgs mechanism. 3. The role of the Higgs field. The Higgs field and its associated particle, the Higgs boson, play a unique role in the Standard Model. The Higgs field permeates the entire universe, giving particles mass by interacting with them. Without the Higgs mechanism, particles would not possess mass, and the world as we know it would be vastly different. 4. Confirmations and challenges. The Standard Model has been an incredibly successful theory, with many of its predictions confirmed by experiments conducted at particle accelerators. Notably, the discovery of the Higgs boson at the Large Hadron Collider in 2012 provided a significant confirmation of the model. However, there are still several unanswered questions, such as the nature of dark matter and the absence of gravity within the framework. Dark matter. One of the most pressing questions in modern physics is the nature of dark matter. Observations of galactic rotation curves suggest the existence of unseen matter that does not interact with light or other known particles. The Standard Model does not provide an explanation for dark matter, leaving scientists to explore alternative theories, such as supersymmetry or extra dimensions. B. Neutrino mass. Although the Standard Model considers neutrinos as massless particles, experiments have shown that they have a tiny but non-zero mass. Understanding the origin of neutrino mass is an active area of research and may require extending the Standard Model or incorporating new physics beyond it. C. Grand Unified Theories. The Standard Model successfully describes 3 of the 4 fundamental forces but does not include gravity. Physicists aim to develop grand unified theories that unify all 3 forces within the Standard Model framework, providing a more complete understanding of the fundamental interactions. D. Quantum gravity. Integrating gravity into the framework of the Standard Model remains an open challenge. Gravity, as described by general relativity, differs significantly from the other fundamental forces and cannot be easily reconciled with quantum mechanics. Unifying gravity with the other forces under a quantum theory is an active area of research, with proposed theories such as string theory and loop quantum gravity. E. Supersymmetry. Supersymmetry is a theoretical framework that introduces new particles, called supersymmetric particles, to the Standard Model. It postulates a symmetry between matter particles and force-carrying particles, providing possible explanations for dark matter and resolving some other questions. However, experiments have not yet confirmed the existence of supersymmetric particles, adding further uncertainties and challenges.